All right, friends, welcome to physics. It's March 8th, new week. In fact, today is the beginning of review week because this Friday we have a test. Last Friday we had a quiz. It went well. Everyone got B or above. There was just one problem that a number of people missed. It says the graph with the red line shows the velocity of an object as a function of time. Which of the green line graphs of kinetic energy versus time matches the velocity data? Okay, so this is velocity versus time. Velocity is getting more and more negative. So that means you're going backwards, you're speeding up. Now, kinetic energy is 1/2 mv squared. The thing to notice here is that if you put in, for instance, a -3 and you square it, you would get a +9. Okay, so that's a little bit of a random example, but the point that I'm trying to make here is that this is always positive. If mass is always positive and speed squared is always positive, your kinetic energy always has to be positive as well. And the v squared shape is going to be a parabola. So there we go. All right, but I was happy with how people did on the quiz. Now, this Friday, you do have a test, and I am happy this week because I have a rather easy week. I just have to write a test, and I don't have to teach you anything because you've already learned it. Or maybe not. Anyway, we'll today I'm going to be going over in a quick and cursory way all of the things that we've done so far in this unit. And I have posted the formula sheet for Unit 2. I encourage you to go take a look at this formula sheet because, so as I said after last test, for the next test, you're going to be getting your Unit 1 formula sheet and your Unit 2 formula sheet, so you can use both. But that means there's a lot of empty space down here on the sheet. So if you come up with things that you want down here, you know, there's my picture of an atom or whatever would make you feel more comfortable to have down there, let me know. And it's your responsibility to know all of these equations, every one of them. So please do that. Okay, what did we do this unit? Well, in the first unit, we just introduced a bunch of terminology, you know. So now you know what velocity is as opposed to speed. You know how to describe things. You knew how to describe things that were moving in a constant acceleration. And that was about it. And then in part 2, in Unit 2, we really ramped things up and we started to try to explain motion. And the way that we explained it was in terms of this conspiracy theory that Newton introduced. Now, I say conspiracy theory because what Aristotle said a long time ago was more closely aligned to what your everyday experience of the world might tell you. He said that if you push on something, you cause it to move. So in Aristotle's world, it's natural for objects not to move. And it's unnatural for them to move, so you start pushing on them. You need to explain why an object is moving. You need to put some force on it. Newton comes along, and this is our modern scientific understanding. He says, it's not that forces cause motion. Motion is itself natural. You don't need to explain why an object is moving. You need to explain why its state of motion is changing. Why is it accelerating? Okay, so Newton's first law says if no force acts on a body, the body's velocity cannot change. That is, the body cannot accelerate. So if you see, so this picture is from a scene from above. You have a little marble that's rolling through this pipe and it comes out and it's rolling along the table. If it's a nice flat table and you don't have any forces on it in the x or y direction, you would expect it to just continue to go straight forever. That's the story that Newton has us believe. And if we see some bending or some shifting in the way that it's moving, if it's slowing down, if it's speeding up, we need to introduce forces to explain it. Now, Newton's second law is what brings in the forces. Newton's second law proposes that forces act like vectors and cause masses to accelerate. The more mass that you have, the harder it is to get something to accelerate. So you can apply the same force to a small mass and get a big acceleration. If you apply that force to a larger mass, you're going to get a smaller acceleration. So that's what you also you could say. The kilogram, here's my kilogram prop. It is about 2.2 pounds. So it's got a little heft. And our idea for a Newton, which is the unit of force, is that if you push on something with a Newton of force for 1 second, it will be going 1 meter per second forever thereafter, until other forces act on it. So you push on it for 1 second with a Newton, and that shows up here in the units. Kilograms times a meter per second for 1 second. So if you push on it with 1 Newton for 1 second, you should get that 1 kilogram to go 1 meter per second. Now, the last part of Newton's conspiracy theory is that we should expect all of our forces to have paired forces. So, for instance, this block is being pulled down by gravity. We presume by Newton's third law that the Earth is being pulled up by this block. How much is it being pulled up? Well, exactly the same amount. So you've got some F force of gravity pulling up on the Earth and the force of gravity pulling down on my kilogram weight. Now, of course, the thing that's that saves this from being an absolutely nuts theory is that you do have this mitigating factor of differing masses. So this doesn't have as much mass as the planet Earth. So when I drop this, it would hurt my knees. It's not as though the Earth comes up to meet that because your F equals ma. Big mass means tiny acceleration. We don't feel the Earth shake. Okay, so let's do a quick example of each one of these types of Newton's laws. Here we have a position of a crate sliding across a frictionless surface, and we plot that as a function of time in this graph. Okay, what is this drawing telling us? It tells us that our object is moving forward at a steady rate. Okay, it's moving the same amount of distance each unit of time. Now, the question is, which one of the force versus distance graphs shown corresponds to it? Is the force getting bigger? Is the force staying the same? Is the force 0? Or is the force increasing and then tailing off? Well, whoops, what am I doing? Oh, I guess I didn't. Well, according to Newton's first law, it has to be this. This has a slope. It has some constant positive velocity, but that slope is not changing. Therefore, there is no net force. So, this is going to be a little confusing later on because, we have this experience of pushing a box across the floor and not having it speed up on us. But in Newton's world, the way that we would explain that is that we have some force of friction that just happens, not as a Newton's third law thing or anything, but it just happens to have the same size as the force that you're pushing forward, and the net force on that is 0. All right, so that's Newton's first law, the type of question that you're gonna encounter this Friday on the test. The Newton's second law types of problems, there's basically 2 types of problems that you should expect to run into. The first type, you saw this as a homework problem some time ago. And in this one, you have 3 astronauts, three forces. So you've got a 32 Newton force at 30 degrees. You have a 55 Newton force right along the x-axis, and you have a 60. And I would write that as a minus 60 degrees because it's below the axis. And that one has a size of 41 newtons. And then I could write this as 30 degrees, 0 degrees, minus 60 degrees. And it asks me what the magnitude and relative direction of the acceleration are going to be. And so I know this is going to be an F net equals ma, and F net is a vector, and a is a vector. So that means my first step in this sort of problem is going to be to write my 3 vectors in component form. So by that I mean, like, for F1, I would do 32 cosine of 30. That would be my x component. And then 32 sine of 30. That would be my y component. And then I would have an x and a y component for F2, an x and a y component for F3. And then to get my F net, I would go ahead and add this plus this plus this would give me my F net x, and then this, the y component of the F1 plus the y component of F2 plus the y component of F3 would give me F of y, and all these forces would continue to be in newtons at that point. But then if I wanted to find my acceleration vector, I would take my F vector divided by the mass of this asteroid, so this 120 kilogram asteroid, and I would divide each component of my F net, and that would then give me an acceleration vector. And if I want to find the size of that acceleration vector, I would have to use my Pythagorean theorem and take the ax squared plus ay squared and take the square root. Okay, so that would be a good kind of short answer question, just to make sure you understand what Newton's law, second law is, and how to apply it. The second type of Newton's second law problem that we looked at was one where you're given some information about the motion of the person, and then you have to infer what sorts of forces are causing that motion. So in this case, you have an 80 kilogram person, and they're experiencing a downward acceleration. So there's our A vector at 2.5. So let's put our y direction vector going up. In this case, our acceleration that we've been given is going to be minus 2.5 meters per second squared, because it's downward. It says, what is the upward force of the parachute on the person? Now, the question came up in class today. If we have this gravitational force, how do we figure out what other forces are on it? Well, you do have to think about the context. So for instance, if this person is on the ground and you're just sitting on a chair or something, you're going to have a normal force pushing up from the chair. So you don't have to leave your common sense behind. You just have to think about things carefully. In this case, you don't have a normal force because this person is not being pushed up by the ground. They're not on the ground. The only thing pulling them up is that tension force from the parachute. And that parachute, this tension force is in this case going to be a little smaller than the force of gravity, and it wants us to find that force. And so what you would do is you'd have your F net. What are your F net? You have tension going up, you have force of gravity going down, so minus the force of gravity. And F net, using your Newton's second law, would be m times A. Tension force, we don't know. Force of gravity is m times g. So in this case, your 80 kilograms times minus 2.5 meters per second squared, kilograms meters per second squared, that's a Newton, equals T minus 80 kilograms times 9.8 meters per second squared. Okay? And so to solve this, you just add 80 times 9.8 to both sides, and that gives you your T in units of newtons. Notice I didn't actually give you the units for things like force and energy and power. Those are not on your equation sheet. So that those units are things that I do expect you to know. If you leave them off, I will take off credit every single time you leave units off. So that's be forewarned. Okay, now Newton's third law is one where every object is met with an equal and opposite reaction. Now, there was this story that I told you about a cart being pulled forward by a horse with a Newton's third law force, and the horse is being pulled backwards with exactly the same amount of force. The two are linked together, so how is it possible for there to be any acceleration? It seems weird. One is being pulled forward, but the other one's being pulled backwards. Well, the way we resolved this paradox is we said, one of the reasons why Newton is able to tell us this story is that we've got this big mitigating factor always with us, which is the Earth. So even if I push myself forward and the Earth rolls backwards, it has a big mass and I don't notice it. So in this story, instead of just having the force of the horse and the wagon, we also have the force of the ground on the horse and the force of the horse on the ground, which is really necessary to understand this because we end up with a net force on the horse, a net force of the horse on the wagon. We have a net force on the horse, which is because the ground is pushing forward on the horse more than the wagon is pulling backwards. And we have a net force on the Earth, which we basically don't notice because the Earth has such a big mass. All right, now, in Unit 2, we also did another thing with forces, and that was to introduce a mechanical model linking types of forces. So we know our gravitational force is mg. If we have a block just laying on a table, we would introduce a normal force, the force pushing up from that surface to counteract the force of gravity pulling down on a block. And as you start to pull that block along the table, if it's not just smoothly going over like on an air hockey table, we have to introduce some sort of a frictional force too. And that frictional force comes from the little temporary atomic bonds that are going on between the atoms in the block and the atoms in the surface. How big is that force going to be? Well, in our model we say it makes sense, and empirically it pretty much works, to be able to link the frictional force to the normal force. And we link it through some number called the coefficient of friction, and that's that mu number. And this coefficient of friction links the two, and it says you're going to have to pull harder on an object that's not moving, and it gives you some maximum force. So if you pull it with 2 newtons, it pulls back with 2 newtons. 3 newtons, pulls back with 3 newtons. 4 newtons, pulls back with 4 newtons. 5 newtons, bam, suddenly you can get it to move the amount of force here is the maximum amount of force that you could pull on a block with and still not get it to move. But once it starts moving, that frictional force is approximately constant, related to the normal force and some smaller coefficient of friction called the coefficient of kinetic friction. And let's do a quick example. Okay, so this next example that I'm going to show you combines the frictional force and the tension force. The tension force is from in a string like this. Okay, so here's a classic problem. This is a machine called an Atwood machine. I think you might be doing something similar to this with Dr. Galava soon in lab. Okay, we have a block H with some mass of 8 kilograms. And we have block S, which has a mass of 3 kilograms. Now, the tricky thing here is that we have introduced some coefficient of friction of 0.7 between this surface and block S. Okay, so if there were no friction, our block S would be pulled down by this block, and the force, the acceleration would be slightly less than 9.8 because the gravitational force from block S is going to not contribute to that acceleration. It's just going to be the gravitational force from block H that's going to contribute. But in this case, it's going to accelerate even less. The acceleration is going to be even smaller because you also have a frictional force. So the forces that matter here, you've got a frictional force. Here's your block S. You've got a frictional force pointing backwards. You have a tension force pulling forwards. And then you have a normal force, and you have a gravitational force. Okay, now for this block S, this gravitational force is known, so that's 3 kilograms times 9.8 newtons per kilogram. Okay, and since the forces are balanced in the y direction, we know that this normal force has to have that same magnitude. We don't know, however, how big the tension force is, and we're going to have to figure it out by linking this to block H. And block H has tension force pulling up, and it has the gravitational force pulling down. And the gravitational force will be pulling down on this block with 8 kilograms times 9.8 newtons per kilogram. Okay? So in this type of a problem, it's asking for the acceleration, but I have two things I don't know. I don't know my acceleration, and I also don't know my tension force. So I'm going to have to write an F equals ma. Oh, and by the way, for my force of friction in this case, I can figure that out pretty easily because my force of friction is going to be mu times the normal force. So it's going to be 0.7 times 3 kilograms times 9.8 newtons per kilogram. Okay, so what would I do here? I'm going to set up my F equals ma in both cases. So my 3 kilograms times A equals tension pulling me forward minus 0.7 times 3 kilograms times 9.8 newtons per kilogram. Okay, so that's my F equals ma is, here's my ma, here's my T minus the frictional force. On the other hand, acceleration is going to be pulling me downward here, so I'm going to bring out my minus sign. Minus 8 kilograms times A equals, here tension is pulling you up, minus the force of gravity, which is just going to be 8 kilograms times 9.8 newtons per kilogram. Now, for me, I look at this and I say, I have basically gotten this problem done. And at most, I would take off 1 point for anything that you do after this on a test, because look at what you have. You have two equations, they are different equations, and two unknowns, A and T. And so just briefly what I would do, I would solve one of these for T. So for instance, you could bring over that, stick that expression in here, and then you would have an equation that just depends on A, and then you can just use algebra to solve for A. Okay, so if you want to practice that with me, please come in and we can do it over office hours. I don't think it's worthwhile to do it right now in the video. All right, so we've done Newton's second law. We've said F equals ma. We've talked about Newton's third law. Centripetal forces is not really a new idea. It's just saying, remember when we talked about in Unit 1 the idea of centripetal acceleration, where an object is going around in a circle, its acceleration is always towards the center of the circle, so its speed is not changing, but it's accelerating all the time. In this unit, all we did with this was to say, what if we start to think about which forces are causing that uniform circular motion? The centripetal forces, it's just F equals ma. What if we put in as our acceleration our v squared over r? And this is, of course, it has to be a net force. And that means that our centripetal acceleration is not a new type of force. It's just a way that forces are acting so as to keep our object moving in a circle. So in this case of the Ferris wheel, for instance, centripetal force could be the sum of the normal force and the gravitational force, or the force from the wall on the person, or whatnot. In this case of the moon going around the Earth, the centripetal force is that of just gravity. That's it. So the centripetal force is a net force. To give you a nice example of this, here's an example from one of your homework sets. I think I might have done this in a previous video, but it doesn't hurt you to see it again. In this problem, you have a car driving at a constant speed over a circular hill and then in a circular valley, and they have the same radius r. At the top of the hill, the normal force on the driver with a car seat is 0. So the only force acting on that person is Fg. They feel very light. They feel as though their stomach is going through their teeth. In this other case, they feel super heavy because they're going through this, and the normal force is having to push them up, and force of gravity will be the same. Now, the thing to notice about this is that in this case, the centripetal force, the force causing this object to go around in a circle, is the gravitational force. In the second case, the centripetal force, the thing that's causing it to go around in this other circle, is the net force, which is the net force that's due to both the normal force and the force of gravity. However, in both of those cases, because that v squared over r is the same, the net force is the same size. It has the same magnitude. It's in different directions. Here the net force is down towards the center of this circle. On the other one, the net force is up towards the center of that circle. But if we say F equals Fg, which would be your mv squared over r, is just going to be your mg. In this other case, you have your F net equals, let me put a net on there, F net equals the normal force minus the gravitational force. And your net force is again going to, so in this case, I guess I could put a minus because you're going down, a minus, okay, no problem. In this case, the net force is going to be going up, so it'd be mv squared over r. So this is F net equals ma. The a is that centripetal acceleration, equals Fn minus same car or same person minus mg. Okay, so then here I can put in, for my mv squared over r, I can put in mg. And I get that my normal force in this case is 2 times m times g. And since I know the mass of the person is 70 kilograms, I know g is 9.8 newtons per kilogram. I can just multiply those two together and take it times 2, and I'm done. Okay, so that's the first approximately 2/3 of Unit 2. Now what we've done at the end of Unit 2 is that we've kind of circled back and asked ourselves, what if instead of just describing everything with forces, we describe things with energy? And this energy has a new type of unit. Remember our forces, it was a Newton is 1 kilogram times meters per second squared. And so our idea was that if we took a Newton and we pushed on it with a force for 1 second, a force of 1 Newton for 1 second, we get that kilogram to go to a speed of 1 meter per second. Now, for energy, we want to think about things in terms of joules. And joules has a unit that's 1 kilogram meters squared over second squared. And the idea here is that what if we took this and we pushed on it with 1 Newton over the distance of 1 meter? So 1 kilogram meter per second squared, that's 1 Newton, times 1 meter. You push on it over a distance of 1 meter, you cause the energy of that object to change. So you start out with some kinetic energy, and this is just 1/2 mv initial squared, and then you push on it for a while with a force that does work on the object. And you end up with some final kinetic energy, 1/2 mv final squared. And so when you do work on an object, you change its energy, and that can be seen either as its change in position or its change in speed. Okay, so in this first way of thinking about it, just without our potential energies, we thought about doing work on an object. If you do positive work, you cause it to speed up. The way you do that is that you push on it in the direction that it's already moving. If you push against it, you would cause the object to slow down, and that does negative work. Okay, so your kinetic energy at the beginning, that's just 1/2 times the mass times the speed squared, you can either cause it to speed up, putting positive work in, or you can cause it to slow down, doing negative work. And so our force ideas and our energy ideas, they are carefully matched. It's not as though we're taking any step here that breaks our physics. It's just we're telling the same story in different terms. And so here's a nice example. This one was from your homework this week. If you have an astronaut and she is being lifted 15 meters, she's going upward, her acceleration is in this direction. Now you could do this all just in terms of forces and your kinematic equations. That would be fine. On the other hand, we can also do this in terms of kinetic energy changing, and our work net is just going to be whatever our net force is times our distance. So this is our displacement. So our displacement, we go up 15 meters. Our net force is also in that direction. How could we find our net force? It would just be the mass of the astronaut. So her mass is 72 kilograms. They tell us that the acceleration is g over 10, so that would be 9.8 divided by 10 meters per second squared. So that's my force, and then if I take that times the distance, it would be 15 meters. That's the net work that has been done on her. Now, what does that matter? Well, from our work energy theorem, 1/2 of her mass times her final speed is the 1/2 mass times her initial speed plus that net work done on her. Okay, so this initial speed is 0, so you can very quickly find out what her final speed is if you just put in her mass. You've got your W net there, and easy. Now, the thing to keep in mind, however, is that net force can also, that net work can also be split into work being done by the helicopter and work being done by the gravitational field. Now, the work being done by the helicopter is a little bit harder to find, but the work done by the gravitational field, so the work of gravity, is just going to be the force of gravity. So that's your mass of the 72 kilograms times 9.8 newtons per kilogram. So that's the force. The displacement is 15 meters. And the angle between these two, because gravity is pulling that way, the force is going down, the displacement is going up, times cosine of 180. So that makes this whole number, that is a -1. So this work of gravity is negative. Now you can see that intuitively if you understand the language that we're using here, because the force of gravity is opposite the direction of her motion. She's going up, force of gravity is pulling down. So this work net is going to be that work of gravity, which is negative, plus the work done by the helicopter, which is going to be positive. So if you want to find out what the work of the helicopter is, you can put this number in for the work of gravity. That will be a negative number. You'll put in the net work right there, which will be a positive number, and you can find the work done by the helicopter. Okay, so there's nothing confusing here except just keeping your language straight. We also talked about power. I'm not going to do any problems with this today because we've done it recently, but keep in mind this is another one of the units that you're going to be responsible for. The amount of power is about how much energy you're dumping into a system per unit time. So it has energy divided by time, joules divided by seconds, has its new unit called a watt. So you have 3 new units that you have to remember for this unit, unit for this unit, okay. The Newton, the joule, and the watt. And we found out that we can write out our power in terms of the force that we're putting on an object times the speed of the object. That would be instantaneous power. And you could also think about average power by looking at the total work being done over some amount of time. Now, in this this last part of the Unit 2, what we've been doing is sort of a radically different way of solving problems, where you think about the force, you kind of stop thinking about the forces, and instead you just think about the energy being stored in one way or another. So for instance, instead of thinking about the work that's being done here, we think of that work that we've put into lifting this up as energy that's being stored in a gravitational field. And we can get that energy back simply by dropping it. And so the way that we've been conceptualizing problems here at the end of the unit is by simply saying we've got a bunch of different types of potential energy. We have the kinetic energy of our object, which is the energy of motion. Potential energy, which are about different types of energy having to do with the position of the object. So raising the object in the gravitational field, squishing a spring, things like that. And the idea is that if we add up all of those types of energy, that can help us, because if we have energy conserved. And we did a bunch of problems with this on Friday. I think we're sort of out of time for today's video, but we'll come back and do a problem or two with it on Wednesday again. So, for instance, here's just a multiple choice question, and the idea is you have a block on a spring. So there's your spring, here's your block. The block, you stretch it out, and in this physics world where there are no frictional forces, they say ignore that. This block will just go back and forth and back and forth and back and forth forever. Okay? And the thing that we want to emphasize here is that the total mechanical energy is constant as the block moves back and forth. So if you take this block at the beginning and you stretch it out 1/2 kx initial squared, you can add up 1/2 kx final squared plus 1/2 mv squared, and it doesn't matter where along the path you pick. It can be right there, 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 there. The x position is different at each one of those places. The speed is different at each one of those places, but somehow adding up all of the energy gives you a constant. So that's the point that the reason why this energy stuff is useful. Here's another one. Suppose you have two people who have the same mass, and they're both climbing to the top of a mountain, and Bill goes straight up, and Alice takes a longer time. She kind of winds around, but they both start out at the bottom and make their way to the top. And it asks, how does the work that Alice did in climbing the mountain compare with the amount that Bill did? Well, the gravitational potential energy is just mgh, and the point of this type of a question is to emphasize that it doesn't really matter. In this case, all that matters is the initial height and the final height. I'm not sure my picture is clear, but this is supposed to be one person climbing straight up the side of the mountain. This is the other person circling around the mountain. Yeah, I don't think I can save it at this point. Okay, so those are our big lessons of Unit 2. Forces cause objects to accelerate. If you have more mass, you accelerate less, but nevertheless. Types of forces like friction and the normal force can be linked to help us solve new problems using Newton's laws. And then finally, we can describe physical situations in terms of force using F equals ma, or in terms of energy, where you add up all the types of potential energy plus the kinetic energy at the beginning equals all the types of potential energy plus the kinetic energy at the end. Okay, so thank you for watching. Please think of some questions if you have them for Wednesday, and we'll be looking to take our test on Friday.